Welcome to NPTEL online course on fractals and multifractals. In the previous lectures, we have discussed the fractal dimension as well as Hausdorff dimensions, and we have seen one example in which the fractal dimension is greater than the Hausdorff dimension, and thereby we drawn some conclusion. Then Hausdorff dimension is always less than or equal to fractal dimension in if you are taking the object in the r power n. Moreover, both are lies between 0 and n, in which Hausdorff dimension is less than or equal to topological dimension, whereas there are some cases both the dimensions are equal. Now we are going to prove some result. Along with the result, one can conclude that when Hausdorff dimension and fractal dimension both are equals. So for that we will discuss the dimension of self-similar sets. So one of the advantages of using an iterated function scheme is that the dimension of the invariant set is often relatively easy to calculate or estimate in terms of the definition of contraction. Consider the case S1, S2 up to Sk is a mapping from r power n to r power n are similarities. That is, with the distance between SIX and SIY is equal to the distance between x and y in term of multiplied with the constant Ci, where Ci lies between 0 and 1. Then Ci is called the ratio of Si. In the contraction mapping, if you are taking the map S from r power n to r power n, in general any space x to x, with the metric space we can take this one metric space with the distance d. If you want to say this is a contraction mapping, then the distance between the images of x and y is less than or equal to c times the distance between x and y. If the c is greater than 0, then we are calling it as the Lipschitz functions. In particular, if c is greater than 0 or greater than or equal to 0, strictly less than 1, we can call this as a contraction mapping. If c is equal to 0, the function becomes the constant mapping in the linear line, so that we are removing the 0 and less than 1, that means not a constant function. If you are taking Ci from 0, 1, if the function satisfying the equation 1, then it is called the mapping. SIs are called the similarities. Thus each Si transform the subset of r power n into the geometrical similar sets. That means if you are taking one set U subset in r power n if you are taking, then if you are finding the image of S under the mapping U, then the set U and S of U are geometrically similar sets. A set that is invariant under such a collection of similarities is called the strictly self-similar set, being a union of a number of smaller similar copies of itself. Say for example, if you are taking closed interval 0, 1 in the Cantor set construction, we can take S1 of x as x by 3 and S2 of x as x by 3 plus 2 by 3. So in the case S1, this maps the interval closed interval 0, 1 to the interval closed interval 0, 1 by 3, and this S2 maps S2 of closed interval 0, 1 goes to 2 by 3, 1. In the same 0, 1 and 0, 1 by 3 are geometrically similar sets. If you are taking the union of these two sets, we can get the first iteration of the Cantor sets. A set that is invariant under such a collection, that means if you are taking Si union of Si of some set A equal to A, then this set I equal to 1 to 2, then set A is called the invariant under a collection of similarity is called the strictly self similarity. Then we can call this set A as a strictly self similar set. That means being a union of a number of smaller similar copies of itself. Standard examples: the middle third Cantor set, the Sierpinski gasket and the Van Koch curve. As we discussed earlier, the Cantor set can be written as the union of two contraction mapping, the Sierpinski triangle written as the union of three mappings, and the Van Koch curve can be written as the union of four mapping that we discussed in the iterated function system theory. So, under certain condition, a self similar set F has the Hausdorff as well as the box counting dimension equal to the value of S satisfying this condition. Sum of I equal to 1 to m, Ci power S equal to 1, that where Ci is the contraction factor of the mapping given mappings. And further that F has a positive and finite S dimensional Hausdorff measure. S has the finite and positive S dimensional Hausdorff measures. If you write F as union of the similarity mapping Fi with the union nearly disjoint, we have that the S dimensional Hausdorff measure of F can be written as union of Hs of Si of F by the scaling property, because Si of F is scaled by the factor Ci. So, by the scaling property of S dimensional Hausdorff measure, we will get Ci power S Hs of F. Here by using this similarity and the scaling property, we will get this equation 3. That means Hs of F can be written as sum of I equal to 1 to m Ci power S Hs of F. That means we need to find the images of all the sets under the mapping, then it is multiplied by the constant factor Ci. On the assumption that Hs of F lies between 0 to infinity at the jump value S, where that Hs jump from the infinity to 0 is called the Hausdorff dimension F, which satisfying the equation number 2. For this argument, to give the right answer, we require a condition that ensuring that the components Si of F do not overlap too much. They are not overlap too much. We say that Si satisfy the open set condition. That means if there exists a non-empty bounded open set V, that V must be a bounded as well as the open set such that Si of V, their union contained in the set V. That means this should be the subset of V with the disjoint union. Then we can say the Si satisfies the open set condition. In the middle Cantor set, the open set condition hold for S1 and S2 with the V as the open set bounded open set as a open interval 0, 1. Suppose Si satisfy the open set condition, the Hausdorff dimension of the invariant set is given in the equation 2. From here we can find the Hausdorff dimension. Now we need to prove that the Hausdorff dimension and topological dimension are same when the mapping satisfying the open set condition. Then we are generating the invariant set under this mapping. Their Hausdorff dimension and topological dimension are same. For that, just I present the theorem. Based on this lemma, one can prove the following theorem. let Vi be a collection of disjoint open subsets of R power n. Vi are collection of disjoint open subsets of R power n such that each Vi contains a ball of radius A1R and is contained in a ball of radius A2R. Vi contains the ball of radius A1R and Vi is contained in the ball of radius A2R. Then any ball B of radius R intersect at most 1 plus 2 times A2 power n time 1 by A1 power n of the closure of Vi bar. So, based on this lemma, one can prove that this theorem. Suppose that the open set condition 4 holds for the similarities Si on R power n with the ratios Ci. There are m number of mapping. Si's are S1, S1, S2 up to Sm number of mapping. Each similarity has the ratio C1, C2 up to Cm. If F is the invariant set satisfying F equal to union of I equal to 1 to m Si of F. That means the HB mapping we are defining. Then we know that Si's are similarity mapping on R power n. So, it is a complete space. Then we can form the hyperspace of R power n. Then you can take F belongs to H of R power n. That means any set A belongs to H of R power n. A element A belongs to H of Rn of n. H is the set of all non-empty compact subsets of R power n. Then we can define the Hutchinson mapping S as S of A equal to union of I equal to 1 to m Si of F, Si of A. Then this union as per the HB theory, the iterated function theorem, this HB mapping has a invariant set. So, associated with the iterated function system, that means this similarity mapping Si, we can find the invariant set. Suppose this exists, that invariant set satisfying this equation, that means S of F equal to F. That means F equal to written as the union of I equal to 1 to m Si of F. Then the box counting dimension of F as well as the topological dimension of F both are equal to S, where the S is the solution of the equation I equal to 1 to m Ci power S equal to 1. Moreover, for this value S, the S dimensional Hausdorff measure is finite, it is lies between 0 to infinity. The S dimensional Hausdorff measure is finite and it is lies between here this 0 to infinity. So, this theorem says that if we have the iterated function system, that means the mapping, if the mapping satisfying the open set condition 4, then if you find the attractor of this mapping, then the Hausdorff dimension and the box counting dimension of the set F is same. Now, let us take the example for this theorem. Say S1 of x equal to x by 3 and S2 of x equal to x by 3 plus 2 by 3. The iterated function system to construct the Cantor set. Both are with the ratio C1, C2 is 1 by 3. Now, we need to check whether this S1, S2 satisfying the open set condition. Both the sets are defined in 0, S1, S2 both are defined in closed interval 0, 1. Now, take the open and bounded set this one 0, 1. Then find the S1 of u, it is 0, 1 by 3 and S2 of u is 2 by 3, 1. Then if you are taking the intersection, it is empty. Also this 0, 1 by 3 and 2 by 3 are disjoint S1 of U intersection S2 of U is empty, disjoint open sets. If you take the union of these two sets 0 comma 1 by 3 and 2 by 3 comma 1 which contained in 0 comma 1. So, it satisfying the open condition given here. We say that Si is satisfying the open set condition if there exists a non-empty bounded open set V such that if you are applying the mapping on this set, this must be contained in the V. Now, we are taking this set and both are contained here, therefore, the open set condition is satisfied by the mapping S1 and S2. So, the invariant set F can be written as S1 of F union S2 of F, that means this invariant set nothing but is the middle third Cantor set. So, if you want to find the box counting dimension or the Hausdorff dimension, we need to solve this equation which we already discussed 2 times, 2 copies of interval of length 1 by 3 power s equal to 1. One time take the ln, then ln 2 into 1 ln of 3 power minus s equal to 1. So, we need to get ln 2 minus s ln 3. So, equal to 0, this side ln 1. So, s one can get as ln 2 by ln 3, that we are writing as 0.6309. So, as per this theorem, so this similarity is satisfying the open set condition and therefore, the dimension of this attractor Cantor set is ln 2 by ln 3. Now, the box counting dimension as well as the Hausdorff dimension both are equal, which is equal to this quantity. Now, we obtained the Cantor set fractal dimension as well as the Hausdorff dimension in the different way of approach. If we construct the invariant set, that means if we obtained the invariant set by means of iterated function system, if the iterated function system satisfying the open set condition, then we can say that the Hausdorff dimension as well as the fractal dimension of the object is same, that can be obtained by this equation. Now, consider the Sierpinski gasket F is constructed from an equilateral triangle by repeatedly removing the interior of the equilateral triangle, one copy. Then there the Hausdorff dimension we already obtained and box counting dimension we obtained, both are obtained by log 3 by log 2. Now, we need 3 mapping, that 3 mapping are the scaled by the 1 by 2, that means the gasket F is the invariant set under the 3 obvious similarity of ratio 1 by 2, which map the triangle E0 onto the triangle of E1. The open set condition holds, taking V as the interior of an E0, because while constructing in the equilateral in the Sierpinski gasket, we will take the interior. We need to take this one, we are removing the interior. Now, we need to take this interior as an V, then it will satisfy the open set condition. Thus, by theorem 1, the Hausdorff dimension and topological dimension of the Sierpinski gasket are both are same and both are ln 3 by ln 2, which is obtained by 3 copies of 1 by 2 size subtriangle. Therefore, power 2 1, then one can apply ln 3 is equal to minus so ln 2, so s equal to ln 3 by ln 2. When applying the logarithmic both side, this will get 0, then one can get s equal to ln 3 by ln 0. So, in that case also the Hausdorff dimension and box counting dimension, then with the fractal dimension, both are equal because all the three mappings satisfy the open set condition. Similarly, in the Van Kachkar also, this is the mapping of the Sierpinski triangle. We are taking the equilateral triangle and dividing three equal parts, dividing the side length as 1 by 2, then joining this point, joining the midpoint, and we are removing the interior, not on the boundary. Then after first step we will get this one, again apply the same mapping on all the three available sets, then one can get this one and different state. After some iteration it will get the F is like this one, Sierpinski gasket. So the box counting dimension and topological dimension both are equal and both are equal to ln 3 by ln 2. Now the modified Van Kachkar. So usually in the Van Kachkar we will take the closed interval 0, n, that means the unit interval length. We will divide three equal parts and remove this one and make it the side of an equilateral triangle. That means like this we will get the curve like this one. This is our one. We will remove this one and make this as a side of an equilateral triangle. Now fix a value which is greater than 0, less than or equal to 1 by 3 and construct a curve f by repeatedly replacing the middle portion a of each interval by the other two sides of an equilateral triangle. I will show in the next figure 2, in which the dimension of f, box counting dimension of f and the Hausdorff dimension of f both are equal, which is the solution of this equation. 2 copies of a power s plus 2 copies of 1 by 2 times 1 minus a power s, which is equal to 1. By solving this one can get the modified Van Kachkar box counting dimension as well as the Hausdorff dimension. Here you can see we are taking the unit interval. So here this interval has a size equal length. The middle interval length is a, which is less than or equal to 1 by 3. Equal to 1 by 3 means we will get the same the triangle. Otherwise we will get this type of curve. So that this side has a 1 minus a by 2, this also 1 minus a by 2, this is a, so that the final length will get a 1. The same procedure you can apply here, divide 3 parts and make it as a side of an equilateral triangle. Here also the length is, usually we will take this side is 1 by 3, this side is 1 by 3, middle also 1 by 3. The middle is now less than or equal to 1 by 3 and making the side of an equilateral triangle. So here to here and here to here we will get the curve like this one. We are giving the different color, not applying any probability, just differentiating it, it gives the different color. So this E1 is applied again and again on all the available interval, then one can get this type of structures. Now the curve f is invariant under the similarity that map the unit interval onto each of the 4 intervals, because we need a 4 mapping, because initially we are taking the unit interval, that is converting here, one mapping for here, one mapping for here, one mapping for here and one other mapping for here. We need the 4 mappings. So the open set condition holds taking V as an isoscale triangle of the base length 1 and the height 1 by 2 times root 3. As per the theorem gives the dimension stated. The dimension is, there is a convenient method of specifying a certain self-similar set diagram mathematically, in particular self-similar curve such as example 2. We can find the dimension here by taking the A as some ratios. Now the same thing here one can see. First I am taking the unit interval. Here this interval I am dividing, and this interval length is 1 by 3 and this interval length is 1 by 3. That means this line segment length is 1 by 3 and this interval length is not 1 by 3, this is 1 by 4 and this is 1 by 4 whereas this interval length is 1 by 3. So, stage in the construction of a fractal curve from a generator, the length of the line segment in the generator are 1 by 3, 1 by 4, 1 by 3, 1 by 4, 1 by 3. Now, again if you have this one, here you can apply 1 by 3, 1 by 3, that line we need to construct like this one. That means 1 by 3 power 2, this is 1 by 3 power 2, this is 1 by 3 power 2, this is 1 by 4, this is 1 by 4 power 2, that means 1 by 4 power 2. In each line segment we can apply this generator, then one can get this type of structure. Again here if you are applying, this length is 1 by 3 power 3 and goes on. So, after certain stage one can get this type of the structure. So, here you can observe that there are 1, 2, 3 copies of the smaller line segment which of size is 1 by 3, and 2 copies their size is 1 by 4, their size is 1 by 4. For mapping this straight line to the here, we need 1, 2, 3, 4, 5 mapping, in which 3 mappings C1, C2, C3 must be equal to 1 by 3, and there must be other 2 more set of similarity, their mapping contraction must be C4 and C5 must be equal to 1 by 4. So, S1, S2, S3 needed to map here and here and here. Here may be S1, here may be S2, here may be S3, and here you can place S4 and S5. So, S4 and S5 ratio must be 1 by 4 and S1, S2, S3 ratio must be 1 by 3. So, you need 5 mapping, all as this copies, then as per our theorem it satisfying the open condition by taking the line segment like here, like this ratio, then for I equal to 1 to 5, Ci power S equal to 1. That means 3 power 1 by 3 power S plus 2 times 1 by 4 power S equal to 1. If you solve this equation, numerically we need to solve, we solve this equation, then one can get the answer is 1.34. So, this is the Hausdorff dimension as well as the box counting dimension of the Koch curve. Similarly, now here the 5 mapping we need to generate this structure. Now, one can consider this structure. Now, we have the curve like this one, unit curve. Here one has there are 1, 2, 3, 4, 5, 6, 7, 8 mappings. We need a 8 mapping. That means this interval you can consider divided at the 4 parts. The scaling is 1 by 4. Scaling is 1 by 4 in the all the interval. So, that means the first interval 1, 2, 3. Now, you just remove this one you have to map like this here. So, I am just erasing this one as here to here and here to here 1, 2, 3, 4. So, one has to map like this one, and instead of going the right side we need to come down and here and here. So, this is the 1, 2, 3, 4 interval. The unit interval is to divide 4 parts. So, we need S1. If you are taking the one unit interval, if we want to construct this generator, we need S1, S2, S3, S4, S5, S6 and S7. One can observe that this is just a we need the rotation mapping, that means the shifting and inverse like this one. So, all the mappings are geometrically similar, S1 to S2, S2 to S3 look like all are the linear scaling. So, all are like a geometrically similar mapping and the similarities mapping. There all the mappings scaling is 1 by 4. So, totally we have 8 mapping. So, 8 mapping of the scaling 1 by 4, therefore, 8 times 1 by 4 power s equal to 1. So, ln 8 by ln 4 get us the dimension of s, that means the dimension of this curve s value. So, this one can write ln 2 power 3 and ln 2 power 2 equal to 3. So, 3 by 2 equal to our 3 by 2 is the s value, that means 1.5 one can get as the fractal dimension. So, here the box counting dimension and the Hausdorff dimension of this curve, this attractor is 1.5. You can see the structure of this curve. Fine. Now, the same thing here we started with the 4 mapping, then this is for the 5 mappings with the 2 different ratios. 1 by 3 is another ratio and 1 by 4 is the another ratio. 2 different ratios means we need to solve this equation numerically. If all are equal ratios means we can solve it manually, that means this method we can use. Here we need to use the numerical solutions for this equation. Now, here you can see again 1, 2, 3, 4, 5 mappings, but all are same scaling, but the scaling one can observe 1, 2, 3. Scaling one can observe it is 1 by 3 only. So, 5 mapping of scaling 1 by 3 power s equal to 1, therefore, one can get the s as ln 5 by ln 3 as a dimension. So, if you generate if you apply this generator on the closed unit interval which length 0, 1 or anything in the line segment, then one can get the curve like this one. So, the fractal dimension as well as the Hausdorff dimension of this set, this attractor is 1.465. Now, you can observe that from this theorem, usually we are generating or constructing the fractal by using the iterated function system. In the iterated function system, x is our space and si's are our contraction mapping for I equal to 1 to n. We have n number of mapping. If n number of contraction mapping, then we can generate the fractal sets. That means the attractor for this iterated function system. If all the mappings are similarity mapping, then one can obtain the fractal dimension of the attractor associated with this iterated function system by using the equation 6. Whereas, now here considering the SI as similarity mapping, but there is a possibility for this mappings are contraction mappings. Now, let us check what is the fractal dimension of the attractor when it is follows the proper contraction mappings. That means, is S1, S2 up to Sm be a m number of contraction on a closed subset D of R power n such that, that means this will contraction mean it will satisfy this equation which is Ci less than or equal to x minus y. That means the image of x and y under the mapping S is less than or equal to distance between x and y times Ci, where Ci is strictly less than 1 and greater than 0. Then here this notation stands for the upper box counting dimension. Then the dimension, Hausdorff dimension of F is less than or equal to S. Similarly, the box counting dimension of F also less than or equal to S, where S satisfying this equation. If the mappings are similarity mapping, this is equal to 1. If the mappings are contraction, this is less than or equal to 1. So, we can propose this proposition. So, it says that S1, S2 up to Sm be a contraction and a closed subset D of R power n such that Bi is satisfying this condition. Bi times modulus of x minus y less than or equal to distance between Si of x and Si of y for Bi lies between 0 and 1 for each I. Suppose that F is invariant for the iterated function system Si, that means this mapping with this union disjoint, then the Hausdorff dimension of this invariant set F is greater than or equal to S, where S satisfying this equation. So, these two propositions and the theorem tells that if you want to construct the fractal with the specific fractal dimension, then how to choose the contraction map factor of an iterated function system. Now, one can note that this theorem states that suppose the open condition is hold for the similarities Si on R power n with the ratio this one, F is the invariant set of this mapping associated with the iterated function this one, then their Hausdorff dimension and topological dimension is equal. Now, the question, what is the converse of this one? Suppose for one attractor F, the box counting dimension and the Hausdorff dimension is same, whether the associated iterated function system will satisfy the open set condition. That means the associated iterated function means the similarity mappings will satisfy the open set condition. For example, consider the S1 is mapping from 0, 1 to 0, 1 and also S2. So, S1 of x is defined as x by 2 and S2 of x we are defining as x by 2 plus 1 by 4, x by 2 by 1 by 4. One can verify both are the similarity mapping. How that if you are finding x1 of x minus S2 of x, one can get x by 2 minus x by 2 which is equal to x by y by 2, then we can get x minus y with the factor 1 by 2. So, for this S1 mapping, the associated C1 is 1 by 2, this is C1. Similarly, for here, so x by 2 plus 1 by 4 minus y by 2 minus 1 by 4, this will cancel. So, one can get 1 by 2 times x minus y. For S2 also, the factor this ratio Ci is, that means 1 by 2. Now, S1 and S2 are similarity mapping on closed interval 0, 1 with the ratio 1 by 2, C1 and C2 both are 1 by 2. Now, just you can think what is the image of these sets. That means, if you are taking the closed interval 0, 1, if you are applying this map S1 on here, it will map the whole interval to x by 2, it is 1 by 2, 0 to 1 by 2. If you are applying this map, it will map to, if you are applying 0, it is 1 by 4. So, here it is 1 by 4 and it will goes up to, if you are applying a 1, 1 by 2 plus 1 by 4 up to 3 by 4. So, if you are that means, if you are applying the S1 of closed interval 0, 1, we can get 0, 1 by 2. If you are applying the S2 mapping, then one can get 1 by 4, the closed interval 1 by 4, 3 by 4. One can get, so 2 plus 1, yes, 3 by 4 one can get. Now, these sets, the image of first one is this mapping 0 to here and image of 0, 1 under the mapping S2 is this one. Now, this portion is overlapping in both the cases. This is overlapping. If you are taking this any open set between here, say for example 1 by 4, 1 by 2, if you are applying this mapping, this is not, the image of this one is not contained in 1 by 4, 1 by 2. Therefore, this S1, S2 is not satisfying the open set condition. Then one can think what is the attractor of this one? This will get the overlapping set. This is the overlapping set. then finally the attractor of this iterated function system, that means 0, 1 together with this S1, the S2, this iterated function system, this similarity, particularly S1, S2 are here, similarity mapping has a attractor. This system has an attractor, then that attractor is of the type is any interval. So obviously if this is the interval, so in that case the Hausdorff dimension, it will give the length, therefore the Hausdorff dimension of the interval is 1. That means this attractor, say for example this has the attractor say F, then the dimension of A is 1, that means the Hausdorff dimension of A is 1, and the dimension box counting dimension of A also we will get 1, whereas for any interval as the dimension 1 in R in the box counting dimension. For we can prove by the covering, we already discussed while proving the box counting method for the interval, the box counting dimension of the interval is 1, any interval in R is 1. So here one can observe that both the Hausdorff dimension and the box counting dimension of the attractor generated by this IFS equal same, whereas this IFS not satisfying the open set condition. That means if open set condition is satisfied by the similarities, then associated invariant set F has a same box counting dimension and Hausdorff dimension. Conversely, if the Hausdorff dimension and the box counting dimension of the set equal to same, then the associated iterated function system or similarity maps need not satisfying the open condition. So it is not a necessary thing to say that it is a satisfying the open set conditions. So this is the counter example for the converse is not true. So from this lecture one can understand that if you want to find the attractor F for the iterated function system, you can construct the iterated function system such a way that the ratio satisfying this one, then the corresponding attractor F as the Hausdorff dimension is greater than or equal to S, which is greater than S. So there are two ways we already discussed in the IFS theory. First one is, if the iterated function system is given, we can find the corresponding attractor, and also in the inverse part, if we give the some attractor, then this attractor will be approximate by the some iterated function system by the Cauchy's theorem we already discussed. Now if the iterated function system is given, if the attractor is generated, if satisfying the open set condition, then the Hausdorff dimension and the box counting dimension both are same. Now I want to generate a fractal with the specific dimension, then we need to construct the iterated function system such a way that satisfying the condition in the proportion 2, then we can generate the fractal which satisfying this equation. That means their Hausdorff dimension is greater than 2. So thank you. One can refer these books for more details. Thanks.